problem solving, our understanding is going to grow. Now these two were simple, sulfurous, sulfuric. Sulfurous, sulfuric. I want to buy the entire space, so let me rub it for once. And you would have wanted to keep things simple. All are dibasic. All are dibasic. So if all are dibasic, they'll have 2 OH groups. Yes or no? Things which I kind of tell you in the beginning of physical chemistry. Equivalent weight discussion, I tell you why S3PO4 is triprotect, S3PO3 is diprotect. Yes or no? So at least you would have wanted to keep things simple. Maximum oxidation number hai, so you want to put 6 arms around sulfur. So dibasic hai, all of them will have 2 OH groups. All of them will have 2 OH groups. And then H2SO3 sulfurous, 2 OH. This is the structure. H2SO4 sulfuric. You can have your own ways, you can have your own ways of recalling structures, but I've always found it useful while drawing H2S2O2. Please be attentive. I've found it useful, while drawing H2S2O2, I've thought of H2SO3. While drawing H2S2O2, I've thought of H2SO3. And don't you think if you replace an oxygen by sulfur, the formula would be H2S2O2? So this might be of help. H2S2O2 is when you replace this double bond O with double bond S. Alright. H2S2O3, and now you'd want to relate it to H2SO4. See out here, if you replace an oxygen by sulfur, and because you know the structure of sulfuric acid for sure, you'll want to remove S double bond O, replace it by S double bond S. You want to keep it simple again, 2 OH because all of them are dibasic. Now this is called thiosulfurous, and this is called thiosulfuric. Thio would stand for sulfur. Thiosulfurous means sulfurous with one more sulfur. Thiosulfuric would mean sulfuric with one more sulfur. Yes or no? So not only the structure, the name would be easy to recall. If you kind of relate H2S2O2 to H2SO3, एक oxygen हटाओ, sulfur लगाओ. If you relate H2S2O3 to H2SO4, fair enough. You call it thiosulfuric, sulfur in sulfuric. Moving on, H2SO4 and H2SO6, H2S2O4, I'm sorry, and H2S2O6 would be symmetrical structures. Again, some of you could draw it correctly. I have seen this is called dithianous. This is called dithianic. Now, when you call it dithianous or dithianic, you kind of putting both sulfur at par. Yes or no? Again, I don't know if it's going to help you or not. But when I hear the term dithianous, I realize that both sulfur are being referred together. Both sulfur are being referred together. Yes or no? Believe me, this is how I've been able to recall dithianous different from thiosulfurous. I've not got confused because thiosulfurous, I know there is a sulfur and the rest is sulfurous. But dithianous, I know both sulfur are at par. Dithianic, both sulfur are at par, and I've thought of symmetrical structure like sulfurous or sulfuric. Got me? H2SO5 or H2SO7 can't be symmetrical because of odd number of oxygen atoms, Now for H2SO5, one end is going to look like sulfuric, another end would look like sulfurous. H2S2O7 would be a structure of this kind. Now this is called pyrosulfurous. This is called pyrosulfurous. The other one is called pyrosulfuric. I'm sorry, it's H2S2O5. H2S2O5 pyrosulfurous. H2S2O7 pyrosulfuric. There's another popular name of this acid. It's called oleum. It's called oleum. So I guess I've kept it simple. Sulfurous sulfuric is known to me. H2S2O2 from H2SO3, H2S2O3 from H2SO4, and that's how I've named the two, pyrosulfurous and thiosulfurous and thiosulfuric. These two are symmetrical, dithianous, dithianic. It sounds like both sulfur are equivalent and the structures are symmetrical. Alright. Now this is pyrosulfurous, this is pyrosulfuric. A couple of acids are left, we'll look into that. Either you go with the average oxidation number calculation, oxygen minus 2, hydrogen plus 1 is going to make it plus 4. This will be plus 6. You all are able to do this. Similarly, minus 4 plus 2, this would be like plus 1 and plus 3. Yes or no? Plus 1 and plus 2, I'm sorry. This is plus 2. Okay? But plus 1 and plus 2, are average oxidation numbers. Both sulfur atoms are non-equivalent. And again, things which I generally teach you in chemical bonding. I guess I told you, from a molecule or from a given part of the molecule, oxidation state could be derived. State could be derived by looking at the neighboring atoms. I mean, even if you don't know the entire molecular formulae, and if they give you a part of the molecule, a large big molecule, looking at the atom, looking at its neighboring bonds, you could arrive at the possible oxidation number. See, a positive oxidation number would be either by complete loss of electrons, but these are covalent compounds. So it has to come out of the bonds getting polarized away from it, the bond getting polarized away from it. So, things again which I told you in 11. Look at this sulfur. Two oxygen atoms around, and both bonds being polarized towards oxygen. This would be plus 2. So the rule would be xy. If y is more electronegative, it's polarized towards y, it's going to bring a charge minus 1 and plus 1. Yes or no? If y is more electronegative, the bond is polarized towards y, and the charge you attribute is minus 1 and plus 1. Fine. So the same concept here, sulfur, two oxygen atoms around it, oxygen being more electronegative is going to pull it away. Because of two oxygen atoms and both the bonds away from sulfur, I'm bringing charge plus 2 over here. For this sulfur, because it's another sulfur atom, the charge would be 0. Now the individual oxidation numbers would be 2 and 0. And what you write as plus 1 is certainly the average oxidation number. Fine. Similarly, you realize both sulfur atoms are not equivalent here. Plus 2 is the average oxidation number, and you could arrive at the individual oxidation numbers by yet again looking at the structure. For this sulfur, you find 4 arms around it. Now by 4 arms, I mean 4 arms with oxygen. And that's going to bring a charge plus 4 over it. I'm not talking of these 2 arms because it's bonded to another sulfur atom, and that's the reason again why the sulfur has individually charged 0. So this plus 2 is because of plus 4 and 0. The same rules, the same approach could be applied to even sulfurous and sulfuric acid. It's plus 4, and if you look at the structure, you'll find sulfur surrounded by 4 arms, all directed away from it. Sulfuric acid, you'll find 6 arms, again all directed away from it. Yes or no? H2S2O4. Now the average oxidation number would be the individual oxidation number because both sulfur are equivalent, and if you get it plus 3, it's plus 3 for both of them. See, 3 arms with oxygen. I will not be considering this arm between identical atoms. For H2S2O6, it's say plus 5 and plus 5 for both sulfur atoms, because again they happen to be equivalent. Also in the structure you find 5 arms around sulfur, all directed away from sulfur. H2S2O5. Well, the average oxidation number might be plus 4. I hope you're getting me. O5 minus 2 each, that's going to be minus 10, plus 2 minus 8. So 2 sulfur accounts for plus 8, which means plus 4 over each of them. I don't know, this plus 4 is the contribution of this sulfur. How much for this? Plus 3. And this is going to be plus 5. Simple to understand. So this plus 4 is because of plus 5 and plus 3. Individual oxidation states. H2S2O7. I'm not calling it symmetrical because of odd number of electrons, but the sulfur atoms look equivalent, and you get plus 6 from usual calculations. You also find the 2 sulfur equivalent. You also find the 2 sulfur equivalent with 6 arms around them, all directed away. All directed away. Fine. So let's move on and complete the structure of the two formulae I gave you. Other than this, H2SO5, H2SO5 and H2S2O8. But again, we have kind of seen these structures before. What is the common name of this acid? Carose acid. Carose acid, chemically also called peroxo monosulfuric acid. Peroxo monosulfuric acid. What is the common name of H2S2O8? Marshall's acid. And again, chemically peroxo disulfuric acid. Again, things which I have told you in class 11. In both of them, you will find the oxidation number exceeding 6. Both of them, the oxidation number would be found more than 6, which you know is not possible. Group number is the maximum possible oxidation number, and thereby you know they will contain peroxo bonds. They will contain peroxo bonds. Yes or no? They contain peroxo bonds. So you will want to draw H2SO5 thinking of H2SO4, and in H2SO4 a peroxo linkage, and this is how it's going to look. Marshall's acid. From H2S2O7 you could derive this structure yet again by drawing a peroxo linkage. So you have a peroxo bond here, and in peroxides, you know, in peroxides the oxidation number of oxygen is minus 1. Well, and again, things which I have told you recently or in the past about arriving at oxidation number by looking at this structure would be the best way to justify. In peroxides, oxygen is minus 1. If you look here, these two oxygen atoms involved in the peroxo bond, well, this can polarize from the right of it, but these two are identical. So, you know, it's going to get polarized from one direction only. Same here, this could polarize the arm with sulfur only. So minus 1 each, whereas this oxygen with OH, you know, is going to polarize from both ends and it's going to be minus 2. So it's also the best possible way of, you know, justifying oxygen being minus 1 in peroxides. We also did it in MOT, if you remember. But these are two particular structures which have been very frequently asked in different exams. Should be there with all of you, and the oxidation numbers will be plus 6, considering minus 1 and not minus 2 for oxygen atoms involved in peroxo bonds. Sulfur is going to be plus 6. It's not plus 7 here, it's not plus 8 here, you know that. And again, I guess I've told you in the past, every time you get an oxidation number more than the expected oxidation number. Every time you get an oxidation number more than the expected oxidation number or more than the group number, even if you are split minded over the structure of the molecule, very frequently you would want to write the maximum oxidation number. I've told you before, जब भी maximum oxidation number से ज़्यादा oxidation number रहेगा, maximum oxidation number put कर देना. It's going to be a very safe guess, because you know, after forming the highest possible oxide, then only it will want to indulge into peroxo bond or formation of peroxides. The limitation is, in our syllabus we have hardly a few peroxides to deal with, but given an opportunity, if you know about more peroxides, you would certainly endorse this, that you know, in all the peroxides the oxidation number would be the maximum oxidation number. Fine. So I wanted you to know the structures of these oxyacids of sulfur inside out. A very popular question is, a very popular question from this part is, they'll ask you which acids have sulfur-sulfur linkage. So many times a question of this kind is there. Which acids have a sulfur-sulfur linkage? It was not there in sulfurous and sulfuric. वहाँ पे तो एक ही sulfur था, है ना? And if you look at the rest of the structures, you will admit from H2S2O2 to H2S2O3, 4, 5 and 6. So basically H2S2, I can write O2 to O6. Keep this in mind, it's going to help. This will help. H2S2O2, O3, O4, O2 to O6 will have sulfur-sulfur linkage. O2 to O6 will have sulfur-sulfur linkage. Happens to be a very popular question, I have told you. And other than this, the only kind of formula which comes to my mind is, I'm sure you all are following me, H2S2O2 to H2S2O6 will be having sulfur-sulfur linkage, and the only formula left would be of this kind, H2SNO6, where N is a variable, H2S3O6, S4O6. Now these are called polythionic acids. Polythionic acids, H2SNO6, where N could be a number, 3, 4, 5. Acids containing 2 sulfur atoms, we concluded H2S2O2 to H2S2O6, but if it's more than 2 sulfur, it's going to have sulfur-sulfur linkage by default. The structure might look like the following: S double bond O, double bond O, OH, and then this would be a chain containing N-2 sulfur atoms. This would be a chain containing N-2 sulfur atoms. All right. So this is how a polythionic acid is going to look like, and will also have sulfur-sulfur linkage. Fine. So this much for today. Although I initially thought I would get started with nitrogen family today itself,